So in this problem, what we have is a descent of a rocket on Mars. Um, and the descent goes into three stages. So there's stage A here, stage B, and stage C. And in stage A, the rocket goes from a speed of 19,300 kilometers per hour to 1,600 kilometers per hour. And that slowdown takes 4 minutes of time. In stage B, Um, I think in stage B it begins at 1,600 kilometers per hour and then slows down to 321 kilometers per hour. And then that slowdown takes 94 seconds. And in stage C, rockets are fired. And, at the beginning of stage C, it'll be at 321 kilometers per hour. And then it reduces to a speed of 0. And it doesn't give you a time. It says that it does that over a distance of 75 meters. Okay, so that's all the stages here. And then in part A, we have to figure out the acceleration during each stage. And in part B, we have to figure out the total distance that the rocket traveled during all three stages combined. Okay, so we're going to do some math work here. I'm going to just get this equation stuff ready. Let's begin by thinking about the setup for stage A. So let me just mark that this is for our analysis for stage A. In stage A, what I want to think about is the velocity. The velocity in here is inconvenient. It's in kilometers per hour. Notice that when we want to calculate the acceleration, it's in meters per second squared. So the hours need to turn into seconds, and the kilometers need to be turned into meters for us to be able to calculate the acceleration during that stage. So what I want to do is I want to take this velocity here, this initial velocity in stage A, and convert it into meters per second. So I'm going to call the velocity in stage A V sub AI, which means that it's the velocity in stage A initial, the initial velocity in stage A. And right now it's 19,300 kilometers per hour. So I'm going to make a conversion there where I'm going to turn it into, I'm going to multiply it by 1,000 over 1 because there's 1,000 meters for every kilometer. And then we know that there's 3,600 seconds in every hour. So I'm going to multiply it by 1 over 3,600. That'll convert the 19,300 into, which was originally in kilometers per hour, into meters per second. So right now this 5,361.111 is the velocity of the rocket initially in stage A. Now I also know that the rocket slows down to a speed of 1,600 kilometers per hour in stage A. I want to convert that final velocity from kilometers per hour into meters per second. So I'll call that velocity stage A final. And that is currently 1,600 kilometers per hour. I'll do the same conversion, converting it to meters, and then converting it into seconds. And then I have 444.4 meters per second. And with those two things, what I'm going to do now is I'm going to use that to calculate the acceleration during stage A. So I'll call the acceleration in stage A A. I'll call it A, 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 the acceleration in stage A. And in order for me to calculate acceleration, it's technically your final velocity minus your initial velocity divided by the time that it takes to do that. So one other thing that I have to do here before I write that is I need to think about the time. The time in here was 4 minutes, and I want that in seconds. And to turn minutes into seconds, I have to multiply the minutes by 60 because there's 60 seconds in a minute. So 4 minutes times 60 seconds per minute gives me 240 seconds. That's the time that we have in stage A, so I'll call it T with a little a subscript in there. 240 seconds. So now I'm ready to calculate my acceleration in stage A. technically that's going to be my velocity in stage A final minus my velocity in stage A initial, all divided by the time that it takes to accomplish that acceleration in stage A. So Desmos automatically pulls all of those numbers in here, and I get an acceleration of negative 20.486 meters per second squared for stage A. So we can take a moment to just write that down, as that's going to be like our part of our answer here. So in question A, in stage A, our acceleration was, now we got to take a moment to think about this. The negative 20.486 meters per second squared, it's negative because the rocket is headed downwards, it's moving downwards, but it's slowing down as it's moving downwards, so the acceleration is actually upwards. So that negative, like I'm basically treating the speed here as positive downwards, and then up is negative. So that's why that 20.486 is negative, but that means it's a negative, but like basically an acceleration upwards. And that kind of makes sense, because if like the rocket is landing and it's like falling as it's landing, and it needs to like fire its rockets, it's basically accelerating upwards as it's getting closer and closer to Mars. So just trying to explain why negative is up, which seems counterintuitive in there. So the acceleration in here is 20, and I'm ignoring the negative sign for now, 0.4, I'll round it to the second decimal place, 0.49 meters per second squared, and I'm just going to write upwards, because that negative in there means that we're accelerating upwards as the rocket is falling downwards to the surface of Mars. Okay, so we're done with that. We're now going to go into analyzing the results from stage B, because we want to get the acceleration there. What do we know? First, what we know is that the initial velocity in stage B is actually the final velocity in stage A. So what I mean by that is the velocity in stage A final is actually going to be the velocity in stage B initial. So I know that those two are equal to each other. Now we want to figure out what the velocity in stage B final is going to be. And that one looks like, see, if you think about what it says here, it finally slows down to 321 kilometers per hour in stage B. So you know that the final velocity here is going to be 321 kilometers per hour. But then I need to convert that into meters per second, so I'll do this standard conversion here. So now we know that the velocity in stage B final is going to be 89.1, I'll call it 89.17 meters per second. That will allow us to calculate the acceleration in stage B. The time in stage B, if you look at it, is 94 seconds. I do not need to change anything about that because it's already in seconds. So now I could calculate the acceleration in stage B. It's technically my velocity in stage B final minus my velocity in stage B initial divided by the time in stage B. Okay, why did that not give me an answer? Okay, let me try this part here. Let me change this part here. Okay, good. So that gave me a number. Now it understands. Okay, so my acceleration in stage B is negative 3.78 meters per second squared. And because it's negative, that really means upwards for me. So going back to here, we need to know stage B acceleration. And the answer for that is not negative, but I'll call it 3.78 meters per second squared, and it's still upwards because the rocket has to fire its engines upwards, accelerate upwards to slow itself down as it's falling into the surface of Mars. Okay, now let's talk about stage C. What do we know about stage C? Stage C is a little different. In stage C, we know that the rocket eventually, the rocket eventually goes to, let's see, the rocket reduces its speed to 0. The distance that it takes to reduce its speed to 0 is 75 meters, and that's a distance, not a time. We also know that at the beginning of stage C, the velocity of the rocket at the beginning of stage C should be the final velocity in stage B, which is whatever 321 is, converted into meters per second. Okay, so let's try to organize this information here. I'm going to say that the velocity in stage C initial is defined as the velocity in stage B final. So that's good. And then we also know that the velocity in stage C final is actually just 0 meters per second because it says that it reduces its speed to 0 as it's doing its final landing there. What else? We also know that the distance that it travels in stage C, which I'll call x sub c, is 75 meters. So you have 75 meters there. And then we need to figure out the acceleration. I think that the most appropriate formula to find the acceleration here is the one that goes like final velocity squared. Let me write it out here. Final velocity squared is equal to initial velocity squared plus 2 times your acceleration and then your delta x, the distance that you travel. This is one of the standard kinematic equations. It connects final velocity with initial velocity, your acceleration, and the distance traveled. And we're going to use this because, well, that's what we have in here. We have an initial velocity in stage C. We have a final velocity in stage C. We have the distance traveled in stage C, and we want to know what the acceleration is. So this formula has everything that we want. I'm going to just kind of rewrite it, though, where, you know, if we use the symbolism that we use for this, this is basically going to say stage C final. This is stage C initial. This is acceleration in stage C, and this is our distance traveled in stage C. Okay, so I'm just putting in the symbolism that I'm using. Also, you know, we do want to rearrange this equation so that way we produce the acceleration in stage C. That's what we're trying to find here. So I guess the first thing that I'm going to do, I'm just going to copy this for a second so that way I can kind of start rearranging it. I'm going to rearrange it where I subtract this quantity from both sides. When I do so, I'll get the final velocity in stage C squared minus the initial velocity in stage C squared is equal to 2 times the acceleration in stage C multiplied by the distance traveled in stage C. Now remember, I'm trying to solve for the acceleration in stage C. So at this point, I'd want to divide both sides by the quantity 2 times the distance in stage C, or 2x sub c. When I do that, so I'm going to just divide by 2 on both sides first. That gets rid of the 2 on the right side. That gives me a 2 right here. Then I'm going to divide by x sub c on both sides. That gets rid of x sub c here, and it makes this x sub c reappear here. And so you can see that we could solve for a sub c, as in the acceleration in stage C, by calculating this formula here. So I'm going to rewrite it like this. And Desmos has already calculated all of this because it knows what the velocity in stage C final is, and it knows the velocity in stage C initial, and it knows the delta x, which is 75 meters. And so it's plugged all of that stuff into the equation, and it gives me this answer of negative 53. So that's the acceleration in stage C. It's 53 meters per second squared upwards. So I'm just going to write that down in our answers here. So for stage C, our acceleration is 53, well, I'm going to round it, meters per second squared, and it's upwards. Okay, so we're done with part A. I want to now talk about the second part to this, which is part B. Here we're supposed to figure out the total distance the rocket traveled across all stages, A, B, and C. Okay, so that's basically what we're going to do is the game plan here is we're going to figure out the distance that it traveled in stage A, the distance it traveled in stage B, and then the distance it traveled in stage C. Okay, let's begin with thinking about the distance traveled in stage A. What we know in stage A is the initial velocity. We know the final velocity. We know the time. So it's possible for us to actually use this version of the equation to calculate the distance traveled. So if we were to kind of go back to the original version of this equation, the generic version of this equation, it just says you take the final velocity, you square it, it's equal to the initial velocity squared plus 2 times your acceleration, and then times delta x, the distance that you travel. What I care about in here is the delta x, like there's the distance that's traveled. So I have to rearrange it where I subtract the initial velocity squared, then I divide by 2 times the acceleration on both sides to get to your distance traveled. And if we're going to do this for stage A, this would be basically like stage A velocity final minus stage A initial, and then 2 times the acceleration in stage A. This will give me the x that was traveled in stage A. And Desmos has already stored those numbers, and that's why you're seeing a calculation in here of 696,666. And that's because like all of these numbers were already stored here, like v, the velocity in stage A initial, velocity in stage A final, the acceleration in stage A. So all those were just copied and pasted into this formula and then calculated there. If we're going to do the distance traveled in stage B, which I'll call x sub b, that would be, just following that formula, the velocity squared for stage B final minus the velocity squared in stage B initial divided by 2 times the acceleration in stage B. And you can see that Desmos is already calculating that. In stage C, the distance traveled is obvious. It's 75 meters because they literally told us that the distance traveled in stage C was 75 meters. Okay, now we want to calculate the total distance, so I'll call that x total. The total distance traveled is, of course, the sum of the distance traveled in stage A, the distance traveled in stage B, and the distance traveled in stage C. Why is this not calculating? Let's see. Well, I'm just... oh. Okay. So I'll just... there we go. I got confused because you got 2 values for C. C is already defined right here, so that's why I didn't have to enter it twice. Okay, so the sum of all of those things is going to be 721,821. And so our answer in here is 721,000 meters. Um, if you wanted to write it in kilometers, you would have to take this whole thing and divide it by 1,000. So we could call it 721 kilometers, 721.8 kilometers for that. Okay, that's the end of that.